Thank you. Okay, well, I'll just get this out of the way right away. This is not a talk about lattices. All right. Okay. No. I know, terrible, right? It's hypocrisy.
Are the codes linear?
We'll see. So this is a talk about interactive coding. This is becoming a more and more active space. So I'm going to feature some works by different combinations of these people, and there's many other interesting works in this space that I'm not going to have time to cover. But this is mostly a talk about not about cryptography, although we get to that a little bit at the end. But I do have adversaries. So yes.
Fix your screen.
What? Oh.
Flux?
Is it flux?
Yeah.
Yeah. So hold on, I have to have my staff help me with this here.
Wow.
Can that stay? Oh, okay, thanks. Okay, so let me tell you about where the adversaries and where the noise come up in this problem. So we're thinking about a setting where we have two-party computation. So two parties are trying to compute some joint function on their inputs. So no secrecy yet. They're not trying to hide anything. They're just trying to efficiently compute some function of x and y. And they're doing this by sending bits back and forth in some interactive protocol. But now we imagine that we can have adversarial noise on this channel. And some bits that are sent might be flipped. And in the most general case, a sender does not know that an error has occurred, and hence if we don't do anything, if we just keep running a protocol that was designed in the noise-free setting, the rest of the computation will be useless. So the entire process of the protocol can depend heavily on the transcript submitted so far. So as soon as there's a single bit flip, a general protocol can get the wrong answer at the end of the computation. And in this setting, we're going to consider a strong adversary who can corrupt a constant fraction of all the bits sent during the course of the protocol. So we're going to fix the length of the protocol. Let's say it's going to be 100 bits. We're going to give the adversary, say, 10%. We're going to give him a budget of 10-bit errors that he can cause at any point in the protocol. So we have a fixed communication length. Now, if this was a constant communication length, we could hope to simply wrap each message in an error-correcting code. But notice here that if we have a long protocol that sends many individual bits, and we have a constant fraction of them can be wrong, then we can't simply wrap each message in an error-correcting code because he could corrupt an entire one of those messages. So if there are m rounds of communication here and his budget is greater than 1 over m for bits that he can flip, then an adversary can defeat just the regular error-correcting coding. So we need something that takes into account this interaction. So this problem was first formalized by Schulman in 1992, who noticed this fact that for m rounds of communication, if I only use sort of error-correcting codes designed for the static setting of communication, I can only achieve an error rate less than 1 over m. So when m is super constant, we want to get something like a constant error rate. And so our goal is to get a constant relative error rate and a constant multiplicative overhead in communication. So if I start with a protocol between two parties that has m rounds of sending a bit back and forth, I want something like a protocol that has 4 m rounds and that achieves, let's say, like a 10% constant error rate. So these are the parameters that I'm trying to achieve. So hope you'll forgive my highly professional slides here that I drew on this, just to give you an idea of what these things look like. So we can express the protocol as a tree. So the most basic way of looking at this is Alice speaks and sends a bit, which is a function of her input y. It's either 0 or 1. That puts us at a new node in the protocol tree as a function of where we are in that tree and of his input. So Bob speaks as a function of his input x and sends 0 or 1. And we can think about executions of these protocols as paths down this protocol tree. So the depth of it's a full binary tree where the depth is the number of rounds of communication. So if we think about execution of the protocols with no errors, we're simply sending bits and traveling down the tree, and we're traversing exactly one path of this tree. So both parties have this internal state that they know what the transcript is so far, they know what they sent, they know what they received. If there are no errors, then there's perfect agreement as to where the two parties are in the protocol tree, and they simply take a path down and reach a leaf, and at the leaves are the answers to their computation. So once we are at a leaf, there's a determined function of the transcript that produces the answer to whatever computation they wanted to compute. So, yes?
So you're only sending 1 bit per message? Is that?
Yes. So I'm assuming, which is without loss of generality under certain regimes of which parameters I care about, that each message is only 1 bit. When messages get longer, interactive coding tends to get easier, at least quantitatively, because I get more protection out of wrapping a long message in an error-correcting code than relative to short messages. So sort of the worst case for us is one bit communication. Okay, so a path in the tree corresponds to a transcript of communication. But when we're trying to simulate such a protocol under errors, what we end up doing is we end up having diverging views of where we are in the tree. So when we have Alice trying to send 0 and it gets flipped to a 1 without her knowledge, then what happens is suddenly we don't have sort of one marker of where we are in the tree. Each internal party has an internal view of where we are in the protocol tree, and these diverge without warning. So Bob's view of where we are is on the left, that a 1 was sent, and Alice's view is that a 0 was sent. So we need some kind of mechanism to detect disagreement in the internally simulated view of the transcript. We need to provide a mechanism to move them back towards the point of agreement, and once they're resynced, to try to proceed again down the protocol tree. So all of the solutions that we'll see for interactive coding follow this general framework that we need some kind of mechanism for Alice and Bob to detect that their internal views are inconsistent, a mechanism to move back in a way that gets them closer to the point where their views diverged, and then once they arrive there, to try to proceed down the protocol tree. And so when there are not errors, we'll make progress in moving back towards agreement and then proceeding down. When there are errors, we may get further and further away, but we will control the pace of that so that when there's a bounded constant rate of error, we can make enough progress that we'll reach agreement at the bottom of the tree. So the way that Schulman formulated this is to think about these as pebble movements. So each party has a pebble that it moves around the protocol tree to represent where it believes in the computation it is. So we can use a simple 4-symbol alphabet for the motions of such a pebble on a binary tree. It either goes down and to the left, it goes down and to the right, it goes up, which, since we're in a tree instead of, say, a circuit, is an unambiguous thing to go up. And we also will have a symbol for hold, which is to stay put at your node in the tree. The reason for this is that we may have a situation where parties are at different levels of the tree. Because parties are moving up and parties are moving down, we can get out of sync as to what level we're at, in which case we want the guy that's higher up to just sort of wait for the other guy to come back to him. So we don't, yes?
They're just 2 parties.
They're just 2 parties. Later in the talk, I'll talk about the n-party case, but at the moment, they're just 2 parties. Okay, and so we're going to describe how pebbles move along one branch of the tree at a time, at most one branch, or stay put. And so the reason that we're going to stipulate that movement is very small is you could imagine a case where, because there have been many errors, parties are really out of sync. So one party is at level 10 of the tree and one party is at level 100. If you detect this, if you sort of have a momentary glimpse where you see that this is the case, you might be tempted to have the guy that's all the way down jump all the way back. This would usually be a bad idea because this view that you have could also be the error. It could also be that you're both correct at a certain point and the adversary makes you think that things are way off. So if you overreact, if you try to correct a lot at once, you're vulnerable to the correction itself being corrupted. So there's no safe moments, there's no bits that are assured to be right. So we always want to take very small, cautious movements so that on aggregate, most of them are in the right direction and we will make progress, but none of them are too big. So when we are wrong, we can only be wrong in a small way. And so the goal is to communicate the sequence of pebble moves so that each party can eventually know at the end of the protocol exactly where the other party's pebble is, and that we make progress and make it all the way down the original protocol tree. So we can think of this in some sense as related to a streaming code problem, where we want to encode a dynamic sequence of characters, left, right, back, and hold, so that it is decoded properly. The entire sequence so far, we want to be decoded properly at special moments in time when there haven't been too high a density of errors in the past. And the global guarantee is that by the end of the protocol will be such a point in time where the past sort of obeys this relative density of error bound. To do this, Schulman presented the first protocol to do this, and he used this very nice combinatorial object called tree codes. So let me tell you how these things work. So a tree code looks confusingly like the protocol tree, but it's a different tree. So it's going to be a binary tree, and I'm going to label its edges with numbers from some constant size alphabet. So in this case, my alphabet is 1, 2, 3, 4, 5. And the goal of a tree code is to pick a labeling of the edges such that any two paths in the tree have a constant fraction of symbols differing if I look at the portion of the path from the lowest common ancestor onwards. So if I take an example here, if I look at these two paths, the first symbol is 4. It's the same for both of them just because they're traveling along the same path, so we don't count that. We look at the sequence of symbols after the paths diverge, and we get these two strings, 1, 2, 5, and 3, 2, 4, which differ in 2 out of 3 symbols. So this is the kind of property we have for a tree code. So note that one thing that this immediately implies is that two siblings of the same parent, we want there to be disagreements in a string of length 1. So therefore, we can never have two edges that are labeled exactly the same coming out of the same node. This is a little bit of an annoyance because it means that simply picking uniformly random labels doesn't work because there's too high a chance of that happening. Yes?
But a parent and a child can have the same label.
Yes, it's possible for a parent and a child to have the same label. Yes. Okay. Any other questions about the definition of this? Yes?
Exactly constant fraction or at least constant fraction?
At least constant fraction. If I have more disagreement, that's great. But I want everything to be bounded from below by the same constant fraction in the amount of disagreement that I have. Other questions? So obviously if I could, for instance, since I am allowing the disagreement to be greater, if I pick a bigger alphabet, my job gets easier. Right? In fact, if I picked an alphabet proportional to the size of the tree, this would be extremely easy. I would just give everything its own label. So the difficulty is getting a constant size alphabet for a tree of, say, polynomial depth. So that's the challenge here. And if I'm going to use this inside an encoding protocol, I also would like there to be, say, an efficient function to compute the label of a given node. Okay, but let's suppose for a moment that we had this kind of object, that we had and by 4 area I don't mean that the number of things in my alphabet to label are 4. I mean that I'm going to have, instead of a binary tree, since I want to encode these 4 possibilities, I'm going to have a tree code where my tree has 4 branches coming out of each node. And let's say that there's some constant size alphabet that I can label it and I can get a tree code. Then I can encode a sequence of these moves, left, right, back, and hold, by the labels of the corresponding edges in the tree code. So I have my sequence of how I'm moving my pebble, and every time I want to make a new move, I'm at a certain point in the tree code corresponding to the sequence I've sent so far, and now I simply send the label of the edge corresponding to my next movement. So what I'm going to send as an encoding of my sequence is going to be the labels of a path down the tree code, where the path in the tree code corresponds to my sequence of pebble movements. Okay, so while I'm going back and hold and up and down in the original protocol tree, I'm going marching down the tree code 1 layer at a time, always sending a next symbol at a new depth. Okay.
So are these messages
Yes.
alternating? So is it
Yes.
or taking turns?
Exactly. So Alice has a tree code and Bob has a tree code, and they each send one symbol. So Alice sends a symbol, Bob tries to decode her sequence of pebble movements, see where she is, decide where he should go, sends a new symbol in his tree code, and they go back and
So
forth.
they're not jointly walking down one tree code.
They can be. Their tree codes can be the same. Yes.
Do these tree codes need to be generated per communication protocol, or?
No, a fixed tree code that is a tree code could be used for all communication ever. So yes, if there existed a nicely, efficiently computable tree code, every protocol could use it. There's no importance to, like, I don't need it to be unpredictable. I just need it to have this good distance disagreement for paths of relative distance property. Other questions?
So for the hold, what do you send when the move is hold?
So I'm thinking about the tree code being on a 4-area tree. So I have 4 edges coming out of each node corresponding to the 4 moves, and I send the label of the corresponding edge.
An example, this is too hard.
I think I might have an example coming up. Maybe not.
So out of a hold,
Right.
if you just held, then in fact the tree repeats, that would have been, under that would be the left, right of the parent siblings somehow.
Yeah, so maybe let me describe an example on this for 2. Let's say I don't use back and hold, I just use left and right. So if I use back and hold, it's just that every node here would have 4 edges coming out, but I would require the same property on pass. So in my sequence of pebbles, I say, okay, at the beginning I want to move left, so I will send a 4.
You want to move left because you're sending a 0.
Yeah, because I'm sending a 0 in the original protocol tree, which is a different tree than this. But let's say I decide, okay, it's the beginning of the protocol. My first bit is 0, so I'm going to move left. So I send the label of the left edge in my tree code. Now we're here. I receive something from the other side. The other person sends something that moves me down in my protocol tree. Okay, and maybe the next time I want to move right, so I send the label in my tree code for a right move.
Wait. You received something, so that means you already moved.
No, not in my tree code. My tree code only corresponds to encoding my sequence of moves. In my protocol tree, so I have two trees. I'm keeping track of where I think I am in the simulated protocol. That's separate from this. This is just my tree to encode my sequence of moves. So so they match up at the beginning. So I'm sending the first bit. I'm moving in both trees. Now I receive a bit. I move in the protocol tree. But I don't move in my tree because this is just my encoding. Now, let's say based on what I heard, I want to move, let's say, right in the protocol tree. Then I would send the label corresponding to the right move here. Now, at some point, based on what the other person is saying, when I'm decoding from their tree code, which I haven't described yet how we decode, let's say I decide that I want to move back in the protocol tree. Then I move my pebble back in the protocol tree, and I still send a forward label edge here. There would be, I would need 3 options. I would send the label corresponding to the back motion in this. So I'm marching down this tree, 1 symbol at a time, every time I'm trying to send a pebble move. Yes?
It's completely unbalanced, because on the paths of the hold, it's much longer than on the path, let's say you went left.
Well, this tree is a perfectly balanced tree. It's just what portions of it I use are due. It is perfectly balanced. It only has to be as long as the total bound on the communication. So if my original protocol was 100 rounds, maybe my error correcting protocol is going to be like a constant times that, let's say 600 rounds. This has to be depth 600 and no longer. Yes?
I guess I'm confused with the intuition about why I should only keep track of my moves on this tree, because it sort of seems like I know what my moves were.
But this is how do I encode to the other party my move in a way that he can decode it when there are errors. And that's the idea of the tree code, is that he's going to look at the sequence of symbols of tree code, and if there aren't too many errors, he's at least going to pick something that has a pretty good common ancestor with what I actually did. So this is not about keeping track of where I am. This is about how do I convey to him my sequence of moves in a robust way.
So
Okay.
if you decided to backpedal, then you don't choose left or right. You choose one of those middle branches and send the label it corresponds to.
Yeah. So this should be. It's hard to draw and actually be able to see. This should be a 4-area tree. Yes.
If you want to move back, then you put the label corresponding to the edge that says I'm moving.
Yeah. So there would be like left, right, back, hold, and I would send the label corresponding. But I'm always moving down in this tree. Whereas my pebble in the protocol tree is moving back, it's holding, it's doing these different. Yes?
I guess you also need another. Oh, you already said that. Never mind.
Okay, so I think it'll help a little if I also talk about how the parties decode and process the messages from other people.
Just last stupid question.
Yeah, sure.
Are you actually sending bits then anymore? Because
I'm sending things from this constant alphabet. If I want to send them as bits, I can write them in binary, and it's up to the constant factors. But that's why constant alphabet, right? Yes. Yes.
More stupid question. How many trees are there and how many columns?
There are 2 trees: the protocol tree and the tree code.
Type of trees.
3 trees.
For the shield.
A tree code for each player. It
my
could be the
tree
same one.
For encoding my symbols, you have your tree for encoding.
But those could be the same. They could be the same.
You know, I walk down my tree, you walk down your tree, which is a communication tree.
Yes,
And we have a communication tree where we both keep track of a pebble with.
Yes, but I prefer to say there are 2 trees and there are 4 views of trees. So there's a protocol tree. We both have our internal view of where we are in it. And there's a tree code tree that we're both sending our own set of symbols down. And your tree code and my tree code could be different, but there's no reason that they need to be. But I'm only sending my symbol moves and you're only sending your symbol moves. Okay. Other questions? All right. Okay. So I'm sending symbols one at a time down the tree code to encode the sequence of pebble moves in the original thing. And okay, what do I do when I receive such a symbol? Well, I keep track of the entire state, the entire sequence of symbols I've received from the other party, and I find the path in the other party's tree code of the proper length that has the closest Hamming distance, symbol by symbol, to the path that I've received so far. Okay, so this is a brute force, inefficient decoding procedure as I've defined it, right? But this is the criterion for decoding. I find the path of the right length that has the closest Hamming distance. Okay, so one technical point. If I think about moving in the protocol tree, and I'm going to, so remember we're going to blow up the communication by a constant. Since some things are going to be wrong, we're going to need to move back. We're going to need to take more time than just a first pass down the protocol tree. Now, if I just worked in the original protocol tree with no motivation, with no modifications, and I get to the very end, and then I hear something that makes me go back, the adversary can win the game by just waiting for the protocol to get to the end and then moving me one node back at the very end, right? So it's a little bit silly. So what we do is we pad the original protocol tree to have a bunch of dummy nodes, simply for the reason that a small error at the end should not actually move us off something that we've been confirming for the last however many rounds of communication. So we're going to work with a padded protocol tree that's artificially longer and just sends dummy messages under whatever leaf node, so that when we move a single node because of like an error at the end, we're just moving under the same dummy node of the original tree, so we don't get a different answer. And this is just a technicality. It's not very hard to do, but it's just so you realize, like, okay, if any error can move the pebble, why is it not that a final pebble move screws up the answer? So this is, yes.
How many dummy layers do we need to add? Constant, logarithm?
It'll be a constant multiplication with respect to the depth. So the original protocol tree will get multiplied by a constant in its depth.
Alternatively, you can think of it as an infinite protocol.
I can think of it as an infinite protocol, and I use as much of it as I want, right? So I don't hold at the end just because I'm at the end, essentially. I keep sort of computing sort of deeper down into like dummy layers of this protocol tree. Okay, so intuition for why does this work? Why is the tree code property a sufficient property for getting the right answer here? So Schulman's analysis is very instructive on this. And what he does is he defines a good event as a moment when both parties correctly decode and know where the other party's pebble is. Okay, so if I have a moment where the sequence of symbols that have been sent in the other party's tree code to me so far, where the path that has the smallest Hamming distance is actually the right path, so I actually get the right sort of node in the tree code, then I know the entire correct sequence of pebble moves that they have sent. Okay, if I'm at exactly the right point in their tree code, I know exactly what their sequence of moves is, left, right, back, hold, etc. So I know exactly where their pebble is. I can simulate that entire sequence, and I know exactly where their pebble is. So if both parties correctly know where the other party's pebble is, then I'm going to claim that they can make progress. In this little moment of time, they can make progress because they either agree on where they are and they can move forward and make forward progress in simulating the protocol, Or they see that they've screwed up and they can make progress towards getting back to a point of agreement where they can move forward. So if we define progress to be how much have we agreed upon minus how far off are we from this moment where we can go back and then to the last point of agreement, that we can make positive progress in this measure at any point in time where we correctly both know where the other party's pebble is. Okay, and a bad event is a decoding error, meaning that I have picked the wrong node in the tree code. I have picked something that is not the right sequence in the tree code. And this can cause me to make anti-progress, in the sense that I can move my pebble in a way that's not helpful. Right? I can go back when I didn't need to go back. I can go forward when I should have gone back. I can go back when I should have held, etc. But this only causes a bounded amount of damage. It only causes me to move like one edge at a time, so I only get an additive constant anti-progress. Okay? So if I look at these moments in time where I have a decoding error, I can sort of classify how bad such an event is by the depth of the decoding error on the tree, which is what I mean is like how high up the tree does it diverge from the correct sequence? The code tree, absolutely, yes. So I get this sequence of symbols in the tree code. I decode to the closest Hamming distance. I look at that point in the tree compared to the real points in the code tree, and I look how far away is the common ancestor of those paths. And that's a measure of how bad my decoding error is. So if I look behind me, if I have that I diverged a sequence of length d, then I know that there has to be a constant fraction of wrong symbols in that recent past up to the common ancestor. Right? Because the property of the tree code is that if I have a long divergence, if I have a very high common ancestor and then long paths coming down in the tree code, then I have a lot of errors. I have a lot of inconsistencies along those paths. So if I have a decoding error of depth L, so L is how far away am I from the common ancestor, so a higher L means a higher point of divergence, then I can look behind me and there's an interval of time that's of length a constant times L, that has a constant fraction of errors. Okay, so I can sort of charge this bad moment to the fact that in my recent past I've had a constant density of errors. And I can set the parameters of the tree code such that this constant density is higher than the global allowed average density the adversary is allowed to spend. Which means that these bad intervals cannot cover too much of the total length of time.
The question so
yes.
The parties need to know the bound on the adversary's
Yes. Yes, they do. And it needs to have a certain relationship with the tree code bound. So we can only get, so with this method, we can only get constant error rates for which we can get tree codes that get better error rates than that. Yes?
In principle, you could guess that or maybe try running parallel protocols with different error rates?
Yes, I would say probably, at least for this approach, and we're going to see better approaches with better constants. But if we only had Schulman, if there had not been all this recent progress, the more limiting factor would be that he only proves tree codes up to a constant of like 1/256. So it's more like how do I get tree codes for those good enough constants more than it is guessing. At least in this framework. But there's been much success on getting better constants. So I'll hopefully have time to get to that a little bit. Okay. So right. So if we have the parameters working out in the right way, we get that these bad intervals can only cover a bounded fraction of all time. Okay, and when we're not in a bad interval, we know we're making progress. And when we are in a bad interval, we have one of these bad events, we're only making, again, a constant rate of anti-progress. So we can play these constants off each other, and we can make progress on average, and we can get to simulate the correct node of our protocol tree. Okay, so that's essentially the analysis.
Well,
yes?
On the other hand, like, it's when would you ever send a hold or a back? I mean, this wasn't quite explained.
So when I'm decoding somebody else's sequence of moves, and so let's say Alice sends the first bit, and she's trying to send 0, but it gets heard as 1, right? At some point, she's going to correctly decode Bob's sequence of moves and see that he simulated this one on his protocol tree that isn't right. So at that point, she's going to want to move them back. She's going to want to get him to go back, and his pebble is trying to follow her pebble. So she's going to move her pebble back to convince him, no, we need to go back to the top of the tree and resimulate this because you moved away that wasn't what I said. And so she sends back she moves her pebble back to get him to come back to meet her so that they can go down together. So they're always trying to keep their pebbles together. And when I send you a forward motion and you mishear it, you're going to take your pebble the wrong way. The mechanism for me to speak up and correct that is to move the pebbles back to the last point that we agreed, and then wait for you to catch up to me.
This is protocol specific or something, though, right? I mean, if there are messages that Alice could send, it doesn't matter. Bob doesn't care about really what they say. You know.
So this is the worst case where the function that every message depends upon the entire sequence of previous messages, which covers all cases. But there could be protocols for which I could take advantage of different structure. But this is for a general protocol. This will work for any protocol, but it won't be optimized for every protocol.
Allison?
Yes.
Still confused. Can you specify exactly what's the protocol, what Alice does in each step and Bob does in each step?
So in each step, they look at the sequence of tree code symbols that they've received from the other person, and they decode it to a point in the tree, the closest Hamming distance, and that corresponds to a sequence of moves: left, right, hold, back. They simulate this to see where the other person's pebble is in the protocol tree, and then they know where their pebble is in the protocol tree. Now, if they're not in the same place, they want to get them back to the same place. So if I'm Alice and my pebble is below Bob's, I want to go back up to meet him. If I'm Alice and my pebble is above Bob's, I want to hold and wait for him to come back to me. If we're in the same place and it's my turn to speak, I will tell him which way to go forward. Okay? Yes?
Can you go back to the previous slide? So is this analysis ever using the length of the interval, or is it just using the fact that there's only a constant fraction of points in time in which there's any interval?
Yeah, it doesn't actually care about the length of the interval.
So the other thing, so if you have like a protocol that on different maybe inputs has different communication complexity,
right.
You always get the worst one, even on the best input, conceivably it can get the worst possible thing. Or
right, so I'm thinking about things in terms of a fixed communication complexity that covers all inputs, right? So yes, it is.
What I'm saying is like, if it's like communication complexity, sometimes you see all strings are not equal right away or something.
Yeah.
You just stop. So if parties are kind of honest, you think it will not preserve the, what is called?
No, it's not. It's not going to preserve that. At least in the way that we're analyzing it now. Whether you could or not, I'm not so sure.
Because I guess I'm just saying here there is a technicality how you count the number of errors. You can always say the attacker is always allowed like a constant fraction of the current transmission as opposed to worst case, because of course if there is some
it's not equivalent in the sense that it makes the problem easier because it's more of a constraint on the attacker. So in that model you could hope to preserve more communication rates, but I'm not working in that model. Okay. So hopefully now I've given you a little appreciation for that tree codes are powerful and tree codes are cool. A bit of bad news. I have no idea how to efficiently construct them. Okay, so there has been some progress on this. And I should say there's also some nice progress on tree codes that can correct noisy errors by Geller, Sahai, and Moitra that looks at a relaxation of the tree code that helps us get efficient constructions. But for adversarial errors, we still, at least with this approach, we still seem to need tree codes that we can't efficiently construct. And randomized constructions are known, but we still want efficient decoding too. Yes. Yes, they have compact representations, but they don't have efficient decoding procedures. So you still have to do this brute force Hamming distance thing, which is not polynomial time in general. Okay, so there isn't a tree code construction. Yes?
Randomized constructions still have polynomial error polynomials, right? Are there any known that have exponential error polynomials?
Exponentially? No, yeah, it's also a polynomial only polynomially small chance of the tree code just not being a tree code. Yes. But even if we say we're willing to live with, okay, something that has 90% chance of being a tree code, and we want efficient decoding, we don't have such a construction. Okay. Amazingly though, cryptographers to the rescue. So Brzezinski and Kalai in 2012 noticed that you actually don't need these long tree codes. So what's hard about a tree code? Why is decoding inefficient for these randomized construction? Well, it's because the tree codes are long. You know, I can brute force a Hamming code on constant size strings, say, or logarithmic size strings. So if we revisit this higher level approach, what do we really need from this? We need a mechanism to detect disagreement. We need a mechanism to move back toward agreement. And we need a mechanism, once resynced, to encode progress down the protocol tree. Okay, so as cryptographers, when we look at bullet 1, provide a mechanism to detect disagreement, something should jump out immediately at us, which is not a tree code, but it's just a hash function. Right? Collision resistant hash. So here's the observation of Brzezinski and Kalai. We can build short tree codes by brute force in polynomial time. Okay? So we can sort of naively concatenate them as a first step. We can use tree code 1 for a while and then start over and use tree code 2, which could be the same tree code. It doesn't really matter. It's just that we're starting fresh on a new tree code that's very short. We're going to run out. We're going to need to swap it out and do a new one and so on. Okay, but what's the problem? Why can't I just stack little tree codes on top of each other? Well, it doesn't actually yield a long tree code. We know that. And so we lose the ability to detect and correct errors in the more distant past. Okay, so if an adversary injects errors all the way down a particular tree code and then you start over encoding the sequence in a new tree code, you have no way of knowing that you're starting from a wrong place. What you're encoding now tells you nothing about the errors that have happened in the past. Okay, so we end up losing memory of things that we need to still correct in the more distant past. But to detect things in the past instead of in the present, we can simply use a hash. So we can hash the entire simulated transcript so far to detect any lingering disagreement in the past when we swap out for a new tree code. Okay, so this is kind of what the Brzezinski-Kalai protocol looks like. I divide the original protocol into smallish chunks, okay, so logarithmic size chunks, let's say, and I use a short tree code to try to simulate each one. And now I do a hash of everything so far to decide, am I happy? Are we in agreement with what we simulated? Or do we want to go back sort of an entire chunk at a time? Okay, so we change from these motions of pebble to pebble, and we sort of have this more general motion of chunk to chunk. Okay, where we try to simulate a chunk internally, we're doing the tree code thing on the chunk, but we're doing it in a local way that we can sort of brute force computationally efficiently. And then we do a hash to see if we want to sort of go forward and do a new chunk or go back and redo an old chunk in which there's been disagreement. Okay, so the properties that they use to do their analysis are they want their hash length to be long enough to avoid collisions with high probability. Okay, if you avoid collisions with high probability over the course of the lifetime of the protocol, then it's very easy to analyze because you can simply do a union bound over the bad events of there being any kind of collisions in the hash, and you can analyze the hash where the case where these hashes always detect all of the disagreements. But notice that we don't, so we want somewhat long hashes to avoid collisions, but we also don't want to blow up the total communication more than a constant factor. So the balance that we want to strike is that these hash phases, when I send across the hash of my value to the other person so that we can try to check and see if we agree, the communication from that shouldn't overwhelm the communication from simulating the regular protocol, because I don't want more than a constant multiplicative overhead. So the balance that they strike is that the total communication of these chunks will match the length of the hash so that these phases are sort of equally weighted. So the amount of communication I spend simulating the protocol is going to be proportional up to a constant factor to the amount of communication I spend doing these hashes. Okay, and since I want hashes to be somewhat long, like logarithmically long, to prevent collisions, I also want my chunks to be sort of logarithmic size. But I can brute force a tree code sort of at those parameters. So I get an efficient protocol that has a with high probability success. Yes?
So the adversary can muck with the hash too, right?
Oh, yes, absolutely. Yeah. So so it's kind of a one-way error in the sense that, let's say that the hashes don't. So wait, there's two ways that he can do this. If the hash doesn't agree, he can make it look like it agrees, right? But to do that, so what is that going to make you do? It's going to make you go forward and do a whole chunk before you get another chance at noticing that you disagree, right? So it sort of costs you one additional chunk before you have an opportunity to correct this again. But the number of errors he has to introduce. So I should say here, and I didn't say, when I'm sending a hash, it's a long message, right? I can wrap it in an error-correcting code. So the number of errors he has to introduce to muck with the hash is proportional to the length of that, just proportional to the length of a chunk. So the amount of anti-progress that I make is proportional to the rate of errors he injects. So I can still make forward progress. So when he does something wrong with the hash, he has to pay for it proportional to a chunk size. And after another chunk, I get another opportunity to correct it. So the amount he throws me off by is proportional to his budget of errors. So I can play the constants off each other and still make average progress.
The hash key is part of the previous chunk? Or
the hash key can be picked freshly random every time and sent along with the error correcting code at the hash phase.
You don't need to do it in the previous chunk.
No, I don't need to. And it'll be unpredictable to him every time. Other questions about this? Yes?
Yeah, I'm just a little bit confused. So if you hash, so what are you hashing? Your part of what you saw him send?
So I'm hashing where I think we are in the protocol tree. So my simulated transcript. So I've gone left, right, and I'm trying to tell him I think we're here, right? That's what I hash. Yes.
In terms of assumptions, do parties have access to shared randomness, or it's
No. Yeah, in this model, there's no shared randomness. Each one simply picks a fresh key for a hash every time and sends that key protected in the error correcting code along with his hash value.
But if you share randomness, you can get much better bounds.
Sorry, yes?
Really randomized for crucial reason, like this protocol. You can't hope to de-randomize it.
Yes, I don't know it's not known how to de-randomize this protocol. So the open question sort of between this and the tree code version, the tree code, once I've picked a tree code, so if I use a randomized construction of a tree code, that's randomized. But once I've picked a tree code, the Schulman protocol is deterministic. Okay, so this protocol does not settle the question, does there exist a polynomial time deterministic protocol? But it's pretty good. I mean, you can get it to succeed with high probability. Okay.
The error rate here is a quarter.
I don't think that's true. I think it's a little worse than that, but it was better than Schulman's, if I recall. Yeah, I don't think it's known to be optimal. I'm going to talk about some recent work of Hoppler that deals with more optimal constants.
So you really have a computational assumption here as well.
No, you don't. You don't. Universal hash. Yeah, everything is information theoretic. If I just have the parties pick fresh randomness for the hash keys every time, this is an information theoretic property still. I don't need to introduce computational assumptions. Okay, so let me tell you a bit of this surprise that sort of happens after you stare at this protocol for a bit. So this is saying, okay, I don't need long tree codes. I can use hashes, right? But I still have these brute force steps. With yes, they're polytime, but it's not sort of the most elegant or the quickest or the simplest protocol that I can hope to do. So sort of what's very funny to me is that it's very easy to stare at this and think that the hashes need to be long so that you avoid collisions. And if hashes need to be long, then chunks need to be long because you need to have this kind of balance. But I think the beginning for the starting point for a new work of Hoppler's that came out in 2014 is that you don't really need these short tree codes at all. We can have a much more more elegant protocol. And the main observation is hash collisions are not so bad. Okay, there's really no reason we have to bend over backwards to make a hash collision a negligible event. That I can certainly understand where Bukursky and Kalai are coming from. That's my very initial tendency too. Like, let's just make them long enough that it never happens and we never have to think about it, right? We do that all the time. But hash collisions are not so bad. It's kind of the same as an error, right? We're already dealing with a constant error rate. Whether it happens because of a hash collision or an attack on the error, or flipping enough bits in the error-correcting code or disrupting the chunk simulation itself, we're already dealing with errors. Why not try to absorb hash collisions at a constant rate as just another constant rate source of error? Okay, and then we can make the chunks constant size, and we don't even need short tree codes. Okay, and since independent hash keys are picked every time, we can still use really powerful concentration bounds like Chernoff bounds to suitably control the overall density of the hash collisions and get nonetheless a very nice bound on the simulation progress. Yes?
Even if you want the hash as constant size, the hash key can it also be made constant size?
It will also be constant size because I'm going to allow a constant probability of collision.
So you're making like everything constant size. And are you like implicitly building a tree code, or it's really different? Maybe this like just.
I have thought about that a lot, and I cannot see how to derive a tree code out of these constructions. I think a lot of us would love to see that, and we don't know how. It seems more like we are separating these problems at least in the randomized setting from tree codes. We do not know how to extract tree codes from these techniques. And there does seem to be at least one explanation, which is that we are using the fresh randomness of these hash keys every time. Tree code doesn't have a deterministic tree code doesn't have that kind of flexibility. Yes.
So maybe you're going to say this, but you still have the issue of trying to figure out how much, what's the nearest Hamming weight code or something, because you've got to go back now and search over the possible.
No, actually. So when my chunks are constant length, I'm not even going to need, if I don't care about the constant rates, if I'm just saying I get a constant rate, and I have a constant rate of error and a constant multiplicative overhead, I actually don't even need to do error correction within the chunk simulations at all. So if a chunk is 10 bits exchanged back and forth, then I just let them all happen as if they're error-free, and then I hash to see if we agree or not. So any 1-bit error injected into that 10 bits will send me off, but I'm just going to make the error rate smaller than 1/10. Now that it's constant, I can just make the error rate smaller than the chunk size, so that he can't even afford to pay 1 bit per chunk, because the chunk size is constant, so his error rate can be bounded below with respect to the chunk size. And now I don't actually have to protect, I don't have to decode anything. I just run the thing as if it's error-free for a small amount of time. I do hashes to correct. And again, now the hash size is also constant length, so I don't even need to wrap them in an error-correcting code, although I should, so I can get better constants, right? But yes.
I mean, so you detect now that, so you disagree, but then how do you fix it?
Yes, excellent question. So this is the thing I'm hiding under the rug because I don't want to get mired in the details of his protocol, because it's much more than this. This is one insight of it, but he does a lot more, and he also talks about optimal constants. But the tricky thing is here, right? Like when the hashes are allowed to be longer, we could also afford to, in the hash phase, say communicate with an error-correcting code an index of what chunk we think we're at, so that we know, like, if we're out of sync, who should go back and who should hold. Here, if we're just sending constants, we can't afford to send an index for where we should go back to, because the number of chunks can be super constant. So Bernard has a more complex procedure for dealing with this, where we sort of vote on where we think we are, and we use more bits of communication to do that, but everything stays within a constant rate. And I'm just not going to go through that procedure because it's more complicated than I'd rather get to interactions of this kind of thing with other applications rather than go through it. But excellent question. Yes, it does get more complicated to figure out who should go back when you don't have enough communication to send an index. Yes. Other questions about this? So this to me is kind of shocking, that we've gone from Schulman in the 90s showing us these beautiful things with tree codes that we had no idea to construct, to somehow realizing in 2014 that we didn't need them in the first place, like at all. And they're still beautiful mathematical objects. I'm sure we will still see work on trying to. And it is also the de-randomization question. So tree codes are a potential way of de-randomizing that we don't know another way to do at this point. But this protocol is kind of amazing to me. Yes, sorry.
But the randomized setting now, this thing is solved.
Yeah.
We can obviously increase hashes.
Yeah, and everything's information theoretic. I don't need any computational assumptions, and I can even, there's even been progress on like the best constants that you can achieve and things like this.
So is it true that any deterministic protocol will give you a tree code?
I don't know that, no. It's an interesting question, but yes, I don't know the answer to that. Okay, so now that we have these really great, efficient, rather simple kinds of protocols, I want to end by talking about what kind of applications might we use this for, and how does this topic of interactive coding sort of intersect with crypto and other things. Okay, so this is the simulated protocol. So let me tell you a little bit about interactive coding meets cryptography. So we can ask this question of, what happens if we want to apply this kind of thing in interactive protocols where we want to preserve more than just correctness and roughly communication complexity? Okay, so the setting we've been talking about so far is that we want the parties to get the right answer and we don't want them to have to communicate for too long. But we haven't preserved any other pieces of the protocol. Like, you can imagine settings like secure multi-party computation where, yes, I want to get the right answer, but I also want to preserve secrecy and privacy of my input, right? So other things we might want to preserve. So there's been some work on this, say the definition of knowledge-preserving interactive coding, which tried to sort of look at this holistically and say, can we ensure that parties don't learn anything more about the other's input than they would have learned in the error-free setting? Okay, so this is a question that's relevant to say, if you could do this, this would immediately allow you to apply this to, say, secure multi-party computation or some such settings. And the answer was no, at least not with the constant error rate. And the main intuition is that this backtracking mechanism, if we think about what we're doing, we're sort of allowing errors to give someone another query at the next message function. Right? So by going back, you get to see what they would have said in a different situation. So you get to sort of probe this other party at more points in the potential protocol tree than a straight path down. Yes?
The negative result is just for information theoretic or also computation?
It's just for information theoretic. Okay. So you can imagine lots of computational solutions to this problem that work actually quite well. So for instance, just signing every message and only answering things when they're signed can sort of force you to only take. So computationally, this problem is much nicer. But information theoretically, which everything so far has been information theoretic, we can't do this with a good error rate. Of course, we can if we're willing to take the sort of 1 over number of rounds hit in the error rate. We can protect each round with an error-correcting code and refuse to go back. So with rate 1 over m, we can do it, but otherwise, information theoretically, we can't. But yes?
Signing, in a usual sense, doesn't quite work because the signing message is at least k bits of security, and so you immediately, if you sign every message and the message is so small, you're immediately paying k cost of the signing, right? So
yeah, so there is some overhead. It's not the error rate that goes up, but there is some overhead in the communication that's additive in the security parameter. But so this
security, because if our messages are even 1 bit, but to sign this one message requires k bits of a signature key. So you are going.
Yeah, you are going to pay for the security parameter. So I don't remember exactly what the parameter trade-off is, but they look at this in the paper and they work out a computational solution that has reasonably good parameters. But so I want to talk a little bit about what we still can do information theoretically. So I want to tell you a little bit about our result for IP equals p space over adversarial channels. So you can ask for a little bit less. Then this knowledge-preserving thing is kind of like almost like a VBB kind of result, right? It feels like it should be impossible because you're asking for a lot. You're asking for them to learn absolutely nothing additional. So we can look at settings where there's specific things we want to hide, but we don't want to hide everything. And in this case, we can get information theoretic solutions. So we can think, for instance, about the problem of IP equals P space over an adversarial channel. Okay, so let's consider for this case that I have a verifier and a prover. And in the error-free setting, the verifier sends challenges and the prover provides responses. Okay, and in IP, we have these protocols that have many rounds. So simply protecting things with an error-correcting code is not going to give us sort of constant rate resilience because we have a super constant number of rounds of challenge and response.
Sorry.
Yes.
Can you clarify what it means IP with adversarial channels? So for completeness and soundness?
Yes. Yeah, so I'm going to define the completeness and the soundness, yes, but that is what I mean. So if I'm now trying to do this prover and verifier protocol over a channel that has this adversarial noise at a constant rate, then I could say simply plug in an interactive coding protocol on top of a proof system. But I might be concerned that I could lose. So I've said that we'll preserve correctness in that case, right? I'll compute exactly the same answer I would have computed. So I would preserve that the verifier would accept honest proofs if I did that concatenation of things. But I would not necessarily preserve soundness, because now the prover can use channel errors as an excuse to back up the verifier and not answer a challenge he didn't want to answer. Right? Like, let's say there's one challenge that, the verifier is going along. He makes a challenge, a dishonest prover doesn't know how to respond. Somebody say, I can't hear you. I didn't hear you. Go back. Right? So we're worried here about, so we already know in some sense how to preserve correctness, how to make it so that an honest prover can still get verified if we use interactive coding. But we don't know how to preserve soundness necessarily. Like, why can a cheating prover not use the excuse of channel errors to convince the verifier of a false statement? Yes?
Assume underlying distribution of the channel error.
So I don't make any assumptions about the distribution of channel error. It's allowed to be adversarial any constant fraction of the total communication.
So I find this a bit counterintuitive. I would have said it's the other way around. Soundness is trivial because if the string is not in the language and the prover cannot convince the verifier, channel errors are not going to convince the verifier. While
but I have to change.
Completeness follows from.
Completeness follows from the interactive coding. So the thing is, because I need to modify the protocol to preserve correct. So as you say, I can think of this as a two-step process. I'm going to need to modify the protocol to preserve correctness. And the problem is, how do I do that modification without destroying soundness? Absolutely, yes.
I think the problem is not that you don't like a challenge, is that you don't want to commit to something that you have said.
Yeah, it's also that, right? I can also say, oh, you misheard my response. Yes, indeed.
Fails in the definition of completeness and soundness, though, when you apply like you have a protocol where, is it because soundness is only probabilistic and completeness is perfect, or?
So you mean why it is just applying an arbitrary interactive coding on top of the? Yeah, I don't know how to show that.
Preserve the correctness if both parties try to preserve correctness. Here you're in the setting that the prover tries to sabotage.
Exactly. Yeah. Mm-hmm. Yeah, because now the prover can use what he's seen because of the coding errors, to purposely move the challenges in a certain direction.
Interactive coding only gives you a transcript, right? And the soundness of the protocol doesn't say that if you get a transcript that verifies, then you cannot cheat.
Yeah, it doesn't preserve the distribution on transcripts is the thing. Like the prover now has control over the transcript in a way he didn't before, so it changes the distribution on transcripts that are produced. Okay, but even though the sort of natural concatenation doesn't work, we can actually, so it turns out we can do this. So we can preserve correctness and soundness over adversarial channel errors, essentially using exactly just the same kind of lightweight techniques of hashing and checking that we can use to do general interactive coding. So the main idea is, what do we have on our side? So we know we can't do this general knowledge preservation, but we do know that when we go back, we know we're going back. So when the prover says, let's rewind, let's go back, let's do a new challenge, the verifier knows what's happening and he can use fresh randomness, and we can use amplification to prevent, say, like a polynomial number of backtracks to really give the prover enough additional advantage. Okay, so we can sort of mute the control of the prover over the transcripts by taking fresh randomness every time we go back, and also using hardness amplification, so that, say, getting sort of like a polynomial number of retries of the challenges doesn't actually give him success in convincing us of a false statement. Yeah, so if it's not a public coins protocol, there you will incur loss in transforming it into a public coins protocol for this. So the trade-off of the rates you will get will be worse.
So can you encode any interactive proof protocol while preserving efficiency?
Yeah. Yes. Yeah. This can work for an arbitrary interactive proof protocol.
And what is the error rate?
The error rate is a constant.
Yes, I know.
What is the constant? I honestly don't remember at all. Yes.
You say that you wanted not to cover this space, but just the NP. Okay, it was an NP second. Couldn't you do that just a PCP thing, or just make sure work on the instance to make sure that you will catch him in many cases?
And you just send the witness. You just send the witness.
Yeah, and anything that doesn't need a super constant number of rounds, I just use an error correcting code and I'm fine. Yeah, it has to need a super constant number of rounds for this problem. Yes. Yes.
Can the prover make things last forever?
No, I'm still going to pick a fixed protocol length and only run for that amount of time, and that also bounds the number of errors that, as a fraction of that he's willing to do. Yeah. Yes. Yes.
Just apply the interactive coding over a restartable sound protocol. Does that maintain soundness?
I have no idea. I haven't thought about it.
Resetability is not an issue here, right? Verifier knows that he has to go back. I mean, it's not like he's being rewound and he doesn't know.
Resetability sound, meaning that if you rewind the prover, then he cannot cheat still.
Sorry, yeah, no, but I'm just.
But this is for
information theoretic.
Yeah, this is. I'm just saying I don't need. Yeah, I can get around needing that.
Effectively, what we do, we kind of explicitly as a first step.
But we do use the fact that you know you're being rewound, I think, which makes things cleaner.
I mean, one thing, I don't know, it's like for Rafi's question about the rate, there is this kind of historical kind of backlash. So I think for interactive coding, people, really care about this constant and so on, but for IP there is this arbitrary constants like 1 thirds, 2 thirds, which are kind of bizarre constants. So talking about, exact constants when you introduce bizarre constants in the definition, it's not clear it's such a meaningful thing.
But the constants in selves are arbitrary and you can make them at smaller details.
Yeah, but that affects exactly error rate.
But that affects these constants, and I mean the relationships are not that lossy. Our constants are not that bad, but I don't remember what they are. Okay, so I'm running out of time, so I'm going to conclude. But I do just want to say, like, there's a bunch of interesting applications further on, for instance, to multi-party protocols. So you can imagine that this gets a lot more interesting in the multi-party case, because I have more than 2 people that I need to sync up. Now that I have n people, when there's an error, n steps sort of need to happen in sync to correct it. So we can look at how these things scale with n, and we can look at different models of communication. So there's been a lot of work on this in multi-party protocols. So I'm not going to go through this. But the main idea is, how do I sync up parties and sort of reduce to the pairwise computations, and what kind of protocols can I get in terms of efficiency? So I want to conclude on a more speculative connection, sort of wondering how all of this, once we get to the multi-party setting, wondering how all of this sort of relates to more general distributed computing against adversarial errors. So recently there was this beautiful protocol of King and Saia for expected polytime Byzantine agreement against a computationally unbounded adaptive asynchronous adversary, so against a really worst-case adversary. So this is, I think, actually a beautiful problem for cryptographers, because we're very naturally pessimistic people who aren't content with sort of constraints on synchrony and constraints on adversaries. And this, I think, is the first thing that gets close to an understanding of what is really the worst-case adversary against which we can do distributed computations. So this is sort of getting close to that. But one feature of their protocol, so I presented an impossibility result that they have still static corruptions of individual parties. So parties that aren't corrupt are always perfect in their communication. So I would like something more that looks like a mobile adversary that corrupts certain parties at certain times but can eventually be everywhere on the network. So I would like to consider a sort of adversary that corrupts a changing set of players. And I showed under a certain model of this that you can't do this. But the more intriguing question is, okay, I can think about a mobile adversary as a network adversary, as errors on the channels, sort of more globally in the protocol. And I'd like to ask the question, adversarial channels can model each of these kinds of adversaries of corrupting parties and corrupting moving parties and just more general adversaries. It's impossible to classify the worst-case adversarial network against which Byzantine agreement is possible. So I think interactive coding for multiple parties has some interesting directions that we can go, both in terms of looking at it maybe in the crypto setting of like secure multi-party computation as people are doing, but also in these more general settings of like what are really worst-case adversaries against which we can hope to get these kind of coordinated distributed computations. So I'd like to stop there. Thanks. Any further questions? Yeah.
Just I guess say a little more about the difference between the VK work and the Hubble work. So it was pretty obvious in the VK work that you use short hash functions. The only reason why you want to make the chunks logarithmic length is exactly because you need to know where you are. So putting the chunk number or something like that, that's the only reason why you need it to be long.
Right.
And this Hubble sort of shows like a very nice way on how to sort of try to keep track of that by only sort of sending little bits of information.
Right. They sort of keep track of that in a more distributed way, yeah.
Yeah. So this is where the log chunks come from.
So my understanding of the adversarial model for the two-party cases, the adversary is only allowed to change symbols, but he's not allowed to introduce new symbols or erase symbols from the channel to try to cause the parties to get out of sync in terms of...
Yes, although actually once we get to the point of the hashing that can sort of reset where you are, that can sort of keep track of where you are, it is we do believe it is resistant to insertion of symbols as well. Because the thing about, like, in the tree code approach, this seemed to go outside the definition of the tree code, because the guarantee is only for strings at exactly the same level of the tree. So when you're decoding a string of the wrong length, you might expect that it should kind of be a recoverable error, but the tree code definition says nothing explicitly about this. But once we get to the hashing, I can hash things of different length, and I'll detect that they're different lengths, and they disagree. So we do believe that these things can be adjusted to deal with that.
You're saying the tree codes actually of Schulman don't work for edit distance if you have like a constant fraction of edit errors?
They're not defined to. They may or may not, but the guarantee that he proves is that things at exactly the same level of tree have this property. He does not prove anything about strings of different lengths.
We just submitted a paper with Mark Braverman and Rangelis extending the definition of tree codes to edit distance, and everything you would expect to go through does go through. Okay.
Yeah, it's just not. It's not an obvious thing from the properties that Schulman proves at all. Yeah.
To define what it means tree code for edit distance.
Do you think the codes actually work? It requires new analysis.
You can define tree codes for edit distance. You can construct them.
And this Hopler thing also works. I mean, everything.
Yeah.
Works?
Yeah.
Well, I don't want to.
It's also not explicitly done in Hopler, but the techniques are relatively robust to these things. Once you don't have this explicit requirement that looks at exactly things of the same length, it seems possible to do this. Yes.
Do you concern the blow-up factor of the communication, or are you satisfied with any polynomial factor?
No, not any polynomial. Constant multiplicative factor of communication. So if I start with a protocol of m rounds, I want a final protocol of 10 n rounds, not m squared.
But he's asking maybe communication, not number of rounds.
They're the same thing. If I'm looking at rounds that have the same number of bits, they're the same thing.
Okay, let's thank the speaker again before.